So for number 21, it says, which of the following is the interval of convergence for the series 1 through infinity for x plus 4 to the n power over n times 5 to the n plus 1. All right, so now to get the interval of convergence, we can use for this the ratio test, which would be pretty convenient for us because we have a power of n for the top and the bottom terms, and we have a base of n. So, and the ratio test says that the limit as n approaches infinity for the absolute value of a sub n plus 1, the next term, over the current term for the series of a sub n, if the absolute value of this entire limit would be less than 1, then the series would be said to be convergent. So to solve for the values of x that make this series convergent, let's first plug everything into this limit expression, and once we simplify as much as we can, let's set whatever's left less than 1 to solve for the x values that would make the series convergent. So we have the limit as n approaches infinity of the absolute value of the next term would be a sub n plus 1. And that just means replace every n occurrence for the series with n plus 1. So we have x plus 4 to the power of n plus 1. Over at the bottom we have n plus 1 times 5 to the power of n plus 1 plus 1, which would be n plus 2. All right, so now that would be the next term, a sub n plus 1, and then we're dividing it by the current series, the current term. And if we're ever dividing by some fraction, we're multiplying by the reciprocal of it. So it should be the reciprocal of the current series. So let's flip the top and the bottom, and that would be n times 5 to the power of n plus 1. Over at the bottom, we have nx plus 4 to the power of n. All right, so now by using properties of exponents, let's simplify everything as much as we can. So the limit as n approaches infinity of the absolute value of x plus 4 to the power of, so since we have an n plus 1 power of x plus 4, we can break it up into x plus 4 to the power of n, then times x plus 4 to the power of 1. And then at the bottom we have n plus 1, and then times 5 to the power of n, times 5 to the power of 2, again using properties of exponents. And then let's bring over the next term, the next part of the limit, n times 5 to the power of n times 5 to the first power, if you break that up, over x plus 4 to the power of n. All right, so now we cross out whichever terms are common. So we have x plus 4 to the n occurs over here and over here, so we can cross them both out. And then 5 to the n occurs here and here, so they're like terms and they can cross out. And 5 to the first over 5 squared, that becomes a first power of 5 at the bottom. All right, so now let's write the simplified version. We have the limit, the limit as n approaches infinity of, let's see what we have left. So at the top of the fraction, we have an n times x plus 4 to the first power. So n and then times x plus 4 to the first power. Over at the bottom, we have a, let's see, 5, and then we have an n plus 1. So 5 times n plus 1. All right, so now the limit pertains to only the values of n. So we can get the limit as n approaches infinity for the n terms, which would be this term over here. We have the n over n plus 1, and any limit to infinity would be the horizontal asymptote for that rational function. And since the top expression for n and the bottom expression for n, both of them have a power of 1. They both have the same power. The horizontal asymptote for that rational function would be the whole number ratio of the coefficients of the top and the bottom n values, which would be 1 over 1. So that entire limit as n approaches infinity for n over n plus 1 would be simply just a 1. Let me put that over here as a side note. And so the limit's done. So what's left would be 1 times the absolute value of x plus 4 over 5. And this would be what we obtained by using the ratio test. Now the ratio test says that the limit as n approaches infinity of a sub n plus 1 over a sub n, this value should be less than 1 for the series to be convergent. Now we have to go on ahead to solving for the x values, which make the series convergent. So let's multiply both of our sides by 5. And that would give us, so these 5's cross out. We have the absolute value of x plus 4 would have to be less than 1 times 5, which is a 5. And now to solve an absolute value inequality, we break it up into two different inequalities, one of which would be x plus 4 would be less than 5. So either you have the same exact thing that we had before, or we would flip over the symbol and take negative of the opposite side. So x plus 4 would be greater than negative 5. And now if we solve both of these one-step inequalities, if we take away 4 on both of our sides, that leaves us with the next value that would be less than 5 minus 4, which is a 1. And in the other case, if you take away 4, then that would be x is going to be greater than negative 5 minus 4, which is a negative 9. Now, we have an initial interval of convergence to be any value of x that's more than negative 9 or less than 1. So as of now, we have x is either going to be more than negative 9 or less than 1, which would be that interval. But we have to check the endpoints and see if the x values of negative 9 or 1 themselves would make the series convergent or divergent. So we have to test the endpoints. Now, if we test when x is equal to negative 9, let's plug in negative 9 for every x in the original series. So we have sigma from 1 through infinity of, let's see, negative. So I'm plugging it in back to the original series for the x value of negative 9. So negative 9 plus 4 to the power of n. Over at the bottom, we have an n times 5 to the power of n plus 1. All right, so that becomes sigma from 1 through infinity of negative 9 plus 4 gives you a negative 5. So that's negative 5 to the n, which we can break that up into negative 1 to the n times 5 to the n. If we separate the bases, it's negative 1 to the n times 5 to the n power. It's the same thing as negative 5 to the n, but we broke it up in terms of their individual values of negative 1 and 5. At the bottom, we have n times 5 to the n times 5 to the first power using properties of exponents once again. And now the common terms of 5 to the n cross out, and we're left with the series from 1 through infinity of negative 1 to the n over 5n. All right, so now we have to use some sort of a test to check if the series would be divergent or convergent. And this would be a convergent series because we have 1 over n. 1 over n would be a harmonic series, which would be divergent. But since we have a negative 1 to the n over 5n, that would be an alternating harmonic series because we have the negative 1 to the n term. So by using the alternating series test, we can say that this series would be convergent. All right, now same thing we would do for x is equal to the other endpoint of 1. Let's plug that in. So sigma from 1 through infinity of positive 1 plus 4 to the n over n times 5 to the power of n plus 1. All right, and that becomes sigma from 1 through infinity of 5 to the n over n times 5 to the n times 5 to the first power. And now the common terms of 5 to the n cross out, and we're left with sigma from 1 through infinity of 1 over 5n. And this would be divergent because we no longer have an alternating harmonic series. We have a regular harmonic series, which by the p-series test would be divergent. All right, so now the interval that we found to be from negative 9 to 1, non-inclusive, would be inclusive at negative 9 because it's a convergent series at the x value of negative 9, but it's going to be non-inclusive at the 1 mark, and that would be our official interval of convergence. So whenever you find any interval of convergence for any series out there, by using the ratio test or the root test, once you get the x values, you want to check the endpoints to see if those values of x themselves would also make the series convergent. And that would be by plugging those endpoints back in for every x and checking to see what type of a series you end up getting. All right, so that would be choice A. All right, so now let's move on to number 22. All right, so number 22. What is the slope of the line tangent to the polar curve r is equal to 3 theta at the point where theta is equal to pi halves? Now, the slope of the tangent line to the polar curve would pretty much be the derivative of the polar function when theta is equal to pi halves. So before we do anything, let's just derive what the derivative would be for a polar function, which you can memorize what the formula is for it, or if you want to come up with it on the spot, that's also fine. So we're looking for dy dx. And now to get dy dx, let's alter it a bit. Let me divide the top and the bottom by d theta, and that becomes dy d theta over dx d theta. Okay. Now, to get what these would be, we know that x is equal to r times cosine of theta. So x is equal to r times cosine of theta. And y is equal to r times sine of theta. So these formulas are used to go from polar form to rectangular form for coordinate points. Let's use these to come up with the derivative for a polar curve. Now, let's get first dy d theta, and that deals with the y function that we have, r sine theta. We want to get the derivative of this y with respect to theta. So r is a function of the radius, and theta would be a function of the angle measure in radians. So these are two different functions, and to get the derivative with respect to theta, we would have to use the product rule for this. So the first function, which is r, its derivative would be r1, but then we have to put the r prime since this would be implicitly defined. So we have r prime, and then times the second function itself, which is sine of theta, and then plus the first function itself, which is r, and then times the second function's derivative, and the derivative of sine of theta would be a cosine of theta. Now let's do the x's. So the derivative of the x function with respect to theta would be r prime for the first function's derivative, and then times the second function itself of cosine of theta. And then we have plus the first function itself, which is r, and then times the second function's derivative, which the derivative for cosine of theta would be a negative sine of theta. And this right here would be the derivative for any polar curve that we want to get the derivative for. Now, before we plug everything in, let's first write out all the parameters. So at theta is equal to pi halves, let's evaluate what r would be. So r at pi halves would be, you plug in pi halves for every theta in the r function. So it should be 3 times pi over 2, meaning 3 pi halves. So we know then that every r term would be 3 pi over 2. Then we want to get the value of sine of pi over 2, sine of theta. And using the unit circle, at the pi halves point, the y value for that would be a 1. So sine of pi halves would be a 1. And then cosine of theta, which is cosine of pi halves, again using the unit circle, would be a 0. All right, so every occurrence of r would be a 3 pi over 2. Every occurrence of sine of theta would be a 1. And every occurrence of cosine of theta would be a 0. Now, r prime would be the derivative of the r function, which is going to be a 3. Okay, so now, if you plug in all these parameters, every occurrence of cosine of theta would be a 0. And that makes our work easier because r times cos theta, which is r times 0, would go away. And so would r prime times cosine of theta also go away. Because 0 times any value would be a 0 at the end. And we're left with r prime sine of theta. Over at the bottom, we have a negative r sine of theta. You know, the sine thetas cross out. And we're left with r prime over negative r. And now let's plug in what these values would be. R prime, we found that to be a 3, over negative r, which is negative of 3 pi over 2. And now positive over negative would be an overall negative symbol. And we have 3 divided by 3 pi halves, which would be 3 times the reciprocal of 3 pi over 2, which is a 2 over 3 pi. And now these 3's cross out, and we're left with an answer of negative 2 over pi. This would be the slope of the polar curve when theta is equal to pi halves. And that corresponds to choice B. Okay, now let's move on to number 23. So the definite integral from 0 through 4 of radical x dx is approximated by a left Riemann sum, a right Riemann sum, and a trapezoidal sum, each with 4 subintervals of equal width. If L is the value of the left Riemann sum, and R is the value of the right Riemann sum, and T is the value for the trapezoidal sum, which of the following inequalities is true? So we want to tell if the left Riemann sum or the right Riemann sum or the trapezoidal sum would be under or over approximations for the real area below the curve from 0 through 4 for radical x. So now to illustrate this idea, let's draw what the function radical x looks like. The function would look something like this. Okay. And now there's 4 subintervals, but let me just put one subinterval for us to get the idea. So if this is one of your subintervals, then let's get a left Riemann sum. A left Riemann sum would be we use the height of the left x value, which is going to be this value, and the height of every rectangle would be the left height, which would be this type of a formation. And this would be an under approximation because the area that's covered by that rectangle is going to leave out some area that we would have got if we got the real sum of all the areas below the curve. So a left Riemann sum would be a heavy under approximation, and then a right Riemann sum. So for a right Riemann sum, we get the right y value, which would be this rectangle, and this covers more area than what we need for the area below the curve. So a right Riemann sum would be a heavy over approximation. So as of now, a left Riemann sum would be an under approximation, and a right Riemann sum would be an over approximation. What about a trapezoidal sum? Well, that would be, we want to form a trapezoid using the left y value and the right y value, which would look something like this. And so since the graph is concave down, some area is not going to be covered. We have a gap over there. Everything below this line is covered, but that small gap over there is not covered. So a trapezoidal sum is still an under approximation, but it's not going to be as much as an under approximation as we had for a left Riemann sum. So the least value that we would be getting would be the value that we get if we perform a left Riemann sum, and then we have a trapezoidal sum, which would be still an under approximation from the real area below the curve. So this would still be less than the real integral from 0 through 4 of radical x dx. And now the biggest sum that we can possibly obtain would be the right Riemann sum, because that covers more area than what we needed. And that would be the order of the sums that we have, which corresponds to, let's see what choice that would be. That would be choice B. So left Riemann sum, and then trapezoidal sum, and the real area, and then the right Riemann sum would be the highest value. Now, whenever we use a left or a right Riemann sum, to check if it's an over or under approximation, that depends on if the original function's increasing or decreasing. And then the trapezoidal sum would depend on if the function's concave down or concave up. But whatever it is, if you just are able to draw out the original function, or if you have some hints to draw out the original function based off of concavity or based off of increasing or decreasing, it's better if you draw it out and check for yourself if any sum would be an under or over approximation, rather than just memorizing all the rules. All right, so number 24. The graph of the piecewise linear function f is shown above. What is the value of the integral from 0 through 12 of f prime of x with respect to x? Now, using the fundamental theory of calculus, the integral of the derivative would just be f of b minus f of a. This would just be f of 12 minus f of 0. And now f of 12, if you look at the function, the graph, f of 12 is a negative 4. It's right there. And then we have a minus f of 0, which is a 4. The y value when x is 0 would be a 4. And negative 4 minus 4 gives us a negative 8. And that would be the answer for this, which corresponds to choice A. All right, so now number 25. The function f has a continuous derivative. If f of 0 is a 1, f of 2 is a 5, and the integral from 0 to 2 of f of x with respect to x is a 7, we want to get the value for the integral from 0 to 2 of x times f prime of x with respect to x. Now, just by looking at this, we know right away that this is a formation that we can apply the integration by parts method to. So we would need a u, and then we would need a v. Okay, so now the u would be the algebraic function that we have of x. Again, choose u to make the derivative of u easier, and the integral of v easier as well. And now v would be the f prime of x dx. Because we know what the integral is for f of x from 0 to 2, we can choose that to be our u. So the v would be, we can choose that to be our v term. V would be whatever is left. So the integral of f prime of x dx would be our v. And now if we derive u, then du would be 1 dx, so just dx. And then v would be the integral of the derivative would be the function itself, which is f of x. All right, now if we plug it into our integration by parts formula, that is uv minus the integral of v du. So uv means x times f of x, so x times f of x, and then minus the integral of v du, which v is f of x, and then du would be dx. All right, so these are bounded from 0 through 2, and these also have a bound from 0 through 2. So we already know what this portion of the integral is. That's given to us. That would be a 7. So let me put the work over here for that. So we will evaluate x times f of x from the upper bound of 2 to the lower bound of 0. So let's plug in the upper bound first. We have 2 times f of 2, and then minus 0 times f of 0, and then minus the integral from 0 through 2 of f of x dx, and that's given right here to be a 7. All right. Now, 0 times any term would be a 0 at the end, so this term crosses out, and we're given what f of 2 is. F of 2 is given to be a 5, and then we bring over the minus 7, and that gives us a 10 minus 7, which would be a 3. And that corresponds to choice A. All right, now number 26. Which of the following series are conditionally convergent? All right, so now to check for conditional convergence, for number 1, we can use for that the ratio test to check if it's absolutely convergent. And if it is, then it's not going to be conditionally convergent. So to use the ratio test, we would plug it into the limit as n approaches infinity of the next term, which is you plug in n plus 1 for every occurrence of n. So negative 1 to the power of n plus 1 over n plus 1 factorial. And then we're dividing by the current series, which would be multiplying by the reciprocal of the current series. And if we flip the top and the bottom for the current series, we then have an n factorial over negative 1 to the power of n. All right, now, if this limit is less than 1, then this series would be absolutely convergent, not conditionally convergent. So now, since we have an absolute value symbol here, the negative 1 terms can cross out. They're not needed. And let's simplify whatever we have left. So this becomes a limit as n approaches infinity of the absolute value of n factorial over at the bottom we have. So to simplify the bottom n plus 1 factorial, we have the first term in that factorial expansion would be n plus 1. Then if we take away 1 from the current term, we're left with n itself, because it's n plus 1 minus 1 factorial. And now these n factorials cross out, and we are left with the limit as n approaches infinity of the absolute value of 1 over n plus 1. Now, any limit to infinity would be that rational function's horizontal asymptote. And since this rational function is bottom heavy, we have a bigger power of n at the bottom than we have at the top. The limit to infinity would be 0 for this. And since 0 is less than 1, this would be an absolutely convergent series. So this is out of our choices because we're looking for a conditionally convergent series. 1, we just proved it to be absolutely convergent using the ratio test. Then let's try 2. So now, using the alternating series test, we can prove it to be convergent, but some series, if it's accompanied with the term negative 1 to the n power, it would be conditionally convergent if we're able to prove that the accompanying series, if we take away the negative 1 to the n power term, if the accompanying series of 1 over radical n, if we can prove that to be divergent, then the alternating series itself would be conditionally convergent, because the condition that the negative 1 to the n term is there would make the series convergent. If that was not there, it would have been divergent. So what that means, if we take away the negative 1 to the n power term, the series becomes sigma from 1 through infinity of 1 over the square root of n. Now, using the p-series test, we know that the power of n at the bottom would be a 1/2, because a square root denotes a power of 1/2. And since 1/2 is less than 1, this would be a divergent series by the p-series test. And so by using the alternating series test, this series would be convergent, because the accompanying series of 1 over radical n would be positive and continuous, and it's decreasing. But the series itself, without the negative 1 to the n power term, would be divergent, and therefore this is going to be a conditionally convergent series. Now, number 3, let's use the same logic. If we get rid of the negative 1 to the n power term, then we're left with sigma from 1 through infinity of 1 over n plus 2. Okay, now, if we compare this to 1 over n, 1 over n is a harmonic series that's known to be divergent using the p-series test, because the power of n at the bottom is a 1. So if we compare this to 1 over n, this would also be divergent by itself. But if we put the negative 1 to the n power term that we had in the very beginning, this series can be proven to be convergent by using the alternating series test. But the accompanying series of 1 over n plus 2, that would be divergent. And that makes this series also a conditionally convergent series. So only choices 2 and 3 would be conditionally convergent, which corresponds to choice C would be the answer for this. All right, so now number 27. Let R be the region in the first quadrant bounded by the graph of y equals to radical x minus 1, the x-axis, and the vertical line x is equal to 10. All right, so before we even finish reading it, let's first draw this out. All right, so we're given that the graph of y equals to radical x minus 1, which would be a shift of right by 1 from the origin for the prime function of radical x, and that would begin right over here, so right by 1 unit. So then that graph looks, a rough sketch would be something like this. All right, so bounded by this curve and the x-axis, which would be, this is the x-axis, and the vertical line x is equal to 10, which let's just say 10 is like here somewhere. That's 1 and that's 10. So we're bounded by this region. X is equal to 10, which would be this line, and that curve. So the region that we're looking at is this region over here. All right, so now it says which of the following integral gives the volume of the solid generated by revolving R about the y-axis. Okay, now we're revolving it about the y-axis, and that means that everything should be in terms of not x's but y's. So this function, which is y equals to radical x minus 1, let's solve this function for the value of x. Now if you square both of our sides, that gives us y squared is equal to x minus 1. And then you would add 1, and that gives you an x function of y squared plus 1. All right, so now this curve would be y squared plus 1 if we're revolving it about the y-axis, and yeah. So now all we do, if we were to revolve this about the y-axis, we want to get the outer radii, which would be the radius formed by the x is equal to 10 curve, and subtract that with the inner radii, which would be bounded by the y-axis and the curve y squared plus 1. And that would correspond to, I believe, D. Let's write down the form, though. So by the disk and washer method, we have the bounds, and it's going to be y bounds for this, which you want to check where the graphs intersect. When would y squared plus 1 intersect the graph of x is equal to 10? If we solve for y, we take away 1 first, and that gives us a y squared value of 9. Then if you take your square root of both of your sides, that gives you a y of positive or negative 3. We're not looking at the negative portion, though. We're looking at the positive portion. That means that the graphs are appearing, or like that region appears from the values of y of 0 up until 3. And those would be the bounds of your integration. So by the disk and washer method, which the volume of the region would be pi, and the integral from a through b of, let's see, f of y. So pi r squared for the outer function. Then we take away the radii for the inner function, which would be g of y's quantity squared with respect to y. Now that f of y function would be the outer radii, which would be, again, the x is equal to 10 function. These would be the outer radii bounded by the x is equal to 10 function. So it should be pi and then times the integral from 0 through 3 of f of y, which would be 10 squared. And then we have a minus g of y, which would be the inner function of y squared plus 1. So y squared plus 1 quantity squared, all with respect to y. And if we simplify that, 10 squared gives you 100, and that would correspond to choice D. Again, pi times the integral from 0 through 3 of 100 minus the quantity of y squared plus 1 squared with respect to y. Whenever you're revolving any solid about the y-axis, you have to make sure that the function is not in terms of x's, but in terms of y's. And then check where the two graphs will intersect in terms of their y values, and those would be the bounds of integration. Then check to see, based off of your drawing, what the outer radius would be and what the inner radius would be. And yes, that would be D. All right, so number 28. So if dx dt is equal to 5 and dy dt is equal to sine of t squared, then d squared y over dx squared is going to be what? So now the second derivative of a parametric function, let's first get the first derivative, right? Which dy dx for a parametric function would be equal to dy dt over dx dt. And now we're given what the dy dt is. It's sine of t squared. And then over at the bottom we have a, let's see, dx dt, which is given to be a 5 already. Okay. Now to get the second derivative, so d squared y over dx squared for a parametrically defined function, we would get the derivative with respect to t, so d dt, of dy dx. Dy dx we just got, so we have to get the derivative of whatever we just got with respect to t. And then over at the bottom we have dx dt, which we already know what that is. All right, now the top portion, let's first get the derivative, d dt, of 1/5 sine of t squared. All right, so that's what the formula says. We first get for the numerator, we get the derivative for the first derivative, and then put that over dx dt, which we already were given that to be a 5. Now for the top portion, the derivative of 1/5 sine of t squared, the general derivative would be 1/5. So the derivative of sine would be cosine, so cosine of t squared. And then we have times the inner function's derivative, the chain rule, which would be 2 times t. And then over at the bottom we have a 5. And that becomes a 2t times cosine of t squared. And then 1/5 divided by 5, these terms combine into 1 over 25. So whatever we have over 25, and that would be the second derivative for our parametrically defined function, which corresponds to choice C. All right, so number 29. All right, so which of the following expressions is equal to the limit as n approaches infinity of 1 over n times 1 over 2 plus n over n? Now we know right away that this is going to be some formation of a Riemann sum. We're going from Riemann sum formation to integral formation. So now the formula for the Riemann sum would be the limit as n approaches infinity of sigma from k is equal to 1 through n of delta x times f of x sub k. Okay, so we know that the f of x sub k would be that term that we have of 1 over 2 plus n over n, and that means that the a value would be a 0. And we know that the delta x corresponds to the 1 over n, and the delta x formula is b minus a, which are your bounds of integration, over n, and that's given to be a 1 over n. And we just said that the a value, the initial value for the lower bound for the integration would be a 0. So b minus 0 over n is equal to 1 over n. And if we solve for b, then the n's cross out. B minus nothing would be a b, and that would be a 1. We know that the bounds of integration would be the a value we just said was 0, and the b value we solved for it to be a 1. And these would be the bounds of integration for the function of 1 over 2 plus x. And that corresponds to choice B. All right, so number 30. A function f has a MacLaurin series given by 2 plus 3x plus x squared plus 1/3 x cubed, and the MacLaurin series converges to f of x for all real numbers x. If g is the function defined by g of x is equal to e to the f of x, what is a coefficient of x squared in the MacLaurin series for g? All right, so now to get the coefficient of x squared in the MacLaurin series for g, let's write down the term that would have a coefficient of x squared for the g of x MacLaurin series. By using the MacLaurin series formula, it should be g double prime at 0, and then times x to the same power as what we had a derivative for, so x squared divided by 2 factorial. All right, now the coefficient of x squared would be simply just a g double prime at 0 over 2 prime term. And for us to get that, we need to know what g double prime at 0 would be. And to get that, we should get the first and second derivatives for g of x, which is defined right here. And then we'll plug in 0 for every x to get g double prime at 0. So g of x is given to be e to the f of x. And now if we calculate the derivative, then g prime of x would be the chain rule, so e to the f of x, and then times the inner function's derivative, which would be f prime of x. All right, so now to get the second derivative, we need to use a product rule because we now have two functions being multiplied. So the first function's derivative, which would be e to the f of x, times the inner function's derivative of f prime of x, and then times the second function itself, which is again f prime of x. So let me just put down f prime of x quantity squared. And then plus we have the first function itself of e to the f of x, and then times the second function's derivative, which is f double prime of x. All right, so now from there, to get g double prime at 0, we plug in 0 for every occurrence of x. And that would be e to the f at 0, and then times the quantity of f prime at 0 squared, and then plus e to the f of 0 times f double prime at 0. All right, so now to get the second derivative of g at the x is equal to 0 point, we need to know what f of 0 is, what f prime at 0 is, and what f double prime at 0 is. And that we can get by using the MacLaurin series expansion for f of x, which is given. So the first term itself would be f of 0, which f of 0 would be simply just a 2, and we're good. Then to get f prime at 0, let's use the second term, which is a 3x. So that 3x was obtained by getting f prime at 0 times x to the first power over 1 factorial, which is just 1, and that happened to be a 3x. All right, now if we solve this equation for the f prime at 0 value, then we would divide by x on both of our sides, and f prime at 0 would be simply just a 3x divided by x, and that would be a 3. All right, now to get the f double prime of 0 value, we set the third term in the series for f of x equal to x squared, which should be what? F double prime at 0 times x squared over 2 factorial, which should just be 2 times 1, which is 2, and that would be equal to x squared. All right, so now from there, we have, if we double both of our sides, that gives us a f double prime at 0 times x squared would be equal to 2x squared. And then if we divide both of our sides by x squared, that leaves us with an f double prime at 0 value of 2. All right, so now that we know what all these values are, let's plug it in for every occurrence of f of 0, f prime at 0, and f double prime at 0 to get g double prime at 0. So we have e to the f of 0, which f of 0 was a 2, and then times f prime at 0, which was a 3 squared, and then plus e to the f of 0, which would be e to the second power, and then times f double prime at 0, which we found that to be a 2. And that simplifies on to 9 e squares plus 2 e squares, and 9 and 2 gives you 11 e squared, would be the second derivative of g at x is equal to 0. All right, so now that we know what the second derivative of g would be at the 0 x value, we can plug it into our term that we're looking for. So g double prime of 0 is 11 e squared, then times x squared over 2 factorial would just be 2. So the coefficient of x squared would be 11 e squared divided by 2, and we found that by plugging it into g double prime at 0, and then dividing that by 2 factorial. And that corresponds to choice D. So 30 should be D.